In this video, we will be reviewing over resistors connected in series and resistors connected in parallel. Beginning with resistors connected in series, we have the diagram here. Resistors are said to be connected in a series when they are chained together in a single line. And since all the current flows through the first resistor has no other way to go, it must also pass through the second resistor, the third resistor, and so on. So that when we calculate resistors connected in series, the total resistors will equal the resistor 1 plus resistor 2 plus resistor 3, and so on. Parallel resistors are resistors in which their terminals are connected to the same two nodes. The equivalent overall resistance is smaller than the smallest parallel resistor. Here we see resistors that are connected in parallel, and so to get their total overall, what we have to do is we have to take 1 over total would equal 1 over the resistance 1 plus 1 over resistance 2 plus 1 over resistance 3, etc. Now we're going to look at how we approach solving resistors connected in series and resistors connected in parallel on this video. So that resistors in series are connected end to end, and they can be replaced by a single equivalent resistance without changing the current in the circuit. And each of the diagrams that you see below is a resistor in a series. Since the current through the series resistor must be the same in each, the total potential difference is the sum of the potential differences across each resistor. We can find the equivalent resistance by saying the equivalent resistance equals resistance 1 plus resistance 2 plus resistance 3. The units will be in ohms. So here we have a problem where we have resistors in series. You can read the problem, but you'll notice that we've identified each of the resistors in the problem, and you'll notice that we're also given the voltage. So we've got our given information, and what we are asked to solve is what is the equivalent resistance for the circuit, and then what current would pass through the resistors. So starting off with our equivalent resistance equals resistors 1 plus resistance 2 plus resistance 3. We can also go back and use our change in voltage equals our current times resistance. This time the resistance will be the equivalent resistance. We can rearrange this so that we can find our current. Now, to get our resistance equivalent, you will notice that our problem gave us kiloohms, and we had to convert those to ohms, where 1 kiloohm equals 1,000 ohms. So we added up the resistance 1, 2, and 3, and we've got our equivalent resistance. Now we can take that and we can plug that and our voltage into our formula, and we can get our current. So that for resistors connected in series, the equivalent resistance should be greater than the largest resistance in the circuit. And if we look at this, our equivalent resistance is greater than our largest resistance in our circuit. Resistors are in parallel when they are across the same potential difference. They can again be replaced by a single equivalent resistance. And so right here, this top diagram, we have our resistance parallel, and below you can see that we've taken those out and we have replaced them with our resistance equivalent. When we solve resistors in parallel, we're using the fact that the potential difference across each of the resistors is the same, and the total current is the sum of the currents in each of the resistors, so that equivalent resistance for resistors in parallel will be right here, where we have 1 over our equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. Now, our units will still be in ohms. Notice that this equation gives you an inverse of the resistance, not the resistance itself. So that when we solve a resistance and parallel problem, you'll notice that we've got the problem here. Now, from the problem, we've identified the volts 1, volts 2, volts 3, and our change in volts. We've identified our currents, and we are asked to identify our R equivalent. Our formula for R equivalent is 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. We still can be using our formulas, change in voltage equals current times resistance. And remember that our resistance will be our resistance equivalence. And so what we're going to do is we're going to take that equation, we're going to rearrange it, and so that we're right over here. Now, what the little n's mean is going to be which voltage and which current we're using. So for our resistance 1, we will have to take our change in volts 1 over our currents 1. We'll get that, and we got those numbers right across there. When we get to resistant 2, again, volts 2 over current 2, we get our answer. Resistance 3, volts 3 over current 3, we got that. Now that we have our resistance 1, 2, and 3, we're going to place those into our equation so that our 1 over equivalent resistance would be our 1 over R1 plus 1 over R2 plus 1 over R3. Now that is going to equal 3 over 3.4. And so we took our 1 over 3.4, 1 over 3.4, 1 over 3.4, added those up, we get 3 over 3.4, divided out, and we get 0.88. Now remember that this gives us the inverse of the resistance, not the resistance. So now what I need to do is I have 1 divided by 0.88, and that's where I get my R equivalent as 1.1 ohms. To get the final current here, we will take our 1.5 volts, which was our total voltage there, divide that by my 1.1 ohms, and then I'll get my 1.4 volts. Now, for resistors that are connected in parallel, the equivalent resistance should be less than the smallest resistance in the circuit. And so 1.1 is smaller than the 3.4.